The Z-axis from the last video is on the machine, and it almost looks like this ball screw is supposed to be there. This bearing is, in ball screw terms, a floating end bearing. It's tiny and noisy because it specifically is not tasked with the axial immobilization of this screw. The only thing that it has to do is prevent the screw wobbling around as it rotates at high speed. Pretend that this shaft is the ball screw. As I rotate the drill, we can see that it's not perfectly straight or balanced. Nothing is ever perfectly straight or balanced. As I speed the drill up, we encounter the first bending mode. The obvious problem with rotor dynamic modes in motion control is that it shakes your shit all over the place. This rotor dynamic mode corresponds with the first mechanical bending resonant mode of a cantilever beam. Through the use of a floating bearing, we can arrest that nasty first mode. Notice that we can accelerate the drill through the speed at which that mode used to occur, and it's gone. In order to do its job, this floating bearing needs a corresponding bore to keep it from moving side to side. This machine came with a bore and a floating bearing for the previous screw assembly. However, as I've tried to illustrate with this bright pink line, that bore is in the wrong location for this new screw and floating bearing. This hole is too far south and it needs to go away. Unfortunately, a hole is by definition an approximately cylindrical nothing, and making nothing go away is nearly always more difficult than making something go away. Nothing is a tremendous problem in industry, and those with the skills to remove it are valuable assets. We call these people welders, and if you meet one, you should buy him a beer.
I'm in no way, shape, or form implying that I'm a welder, nor do I have any formal training or certification as such. However, if mistaken for a welder, I will gladly accept a beer.
The problem with aluminum is that it's an excellent conductor of heat. That means that if you put a joule of heat, that's a unit of heat energy, right here, it's not going to stay there for very long. A joule per second equals a watt. And the rate at which that heat is conducted away into the aluminum in terms of joules per second per some unit of volume or whatever is much higher than in other materials. So if that joule of heat energy doesn't want to stick around for very long, that means we need to keep replacing it. That's a complicated way of saying that since the intro of this video, I bought a new welder. It's got lots of watts. I also made this thing. This is just a Harbor Freight auto-darkening welding lens that's in a printed plastic body, and I gutted a lens shade for my camera and glued it in there. So that'll allow me to bring you along for the ride. There are two excuses that I'm going to use as to why this is a terrible weld. First of all, I suspect that this plate is 3/4 inch thick mic 6, and that's a type of cast aluminum plate that's very stable, but also very full of impurities that like to spatter and mess with your weld. Second, I don't have a chair yet. That's a really stupid excuse, but I'm rolling with it. The moment back at the mill, and a little light sanding, and that hole is gone. Now you can see sort of the shadow of the filler material if the light catches it just right, but that's all that's left. And yes, that was the pretty side. Commensurate with the time and effort that it took to move that hole there, I can almost certify that it's in the wrong spot. Let's go find out. Holy shit, it actually fits. Not only that, but it fits pretty well. In fact, even when it is 35 degrees in the garage, it will fall under its own gravity. And that concludes this lesson on the hard way to move a hole from one place to another.